All right, welcome to a new episode or a new meeting, Journal Club, the fourth one from the Clinical AI Academy. And today we have an interesting paper titled The Illusion of Readiness Stress Testing Large Frontier Models on Multimodal Medical Benchmarks from Microsoft Research by Yu Go et al. So it's a preprint, as you can see, on archives. And still going under peer review. I don't know if it's going to be published or not, but let's go and try. Let's go through it basically, and let's first read the abstract together. So, okay. So the abstract reads as follows. Large frontier models like GPT-5 now achieve top scores on medical benchmarks. But our stress tests tell a different story. Leading systems often guess correctly even when key inputs like images are removed, flip answers under trivial prompt changes, and fabricate convincing yet flawed reasoning. These aren't glitches, they expose how today's benchmarks reward test-taking tricks over medical understanding. We evaluate 6 flagship models across 6 widely used benchmarks and find that high leaderboard scores hide brittleness and shortcut learning. Through clinician-guided rubric evaluation, we show that benchmarks vary widely in what they truly measure, yet are treated interchangeably. Masking failure modes. We caution that medical benchmark scores do not directly reflect real-world readiness. If we want AI to earn trust in healthcare, we must demand more than leaderboard wins and must hold systems accountable for robustness, sound reasoning, and alignment with real medical demands. Right, sounds like a very promising paper to dig deeper into. So I asked ChatGPT to kind of give a summary of the paper so we can have an overview. So the background and motivation, as we have read from the abstract, is basically large language models, for example, GPT-5 or Gemini, can answer or like perform really well on top medical multimodal benchmarks. But these benchmarks where you're testing the models do not reflect real world readiness. And that's what the authors are arguing, so that it's trying to, it's giving the answers based on memorizing and shortcuts, test taking shortcuts, which is not the genuine medical understanding you want from such AI. So they did is stress those models, and what they found that actually they are stiff, brittle, and they're fabricating their answers or fabricated reasoning. The methods, so they tested GPT-5, Gemini 2.5 Pro, OpenAI O3, OpenAI O4 Mini, GPT-4o, DeepSeek VL2. So that is like 6 top tier frontier models. And then benchmarks that they tested those models on were the New England Journal benchmark, JAMA, VQA RAD, PMC VQA, OmniMed, Mimic, Chest X-ray. So top leading datasets or benchmarks to test models on. And what they did is stress tests, 6 stress tests, T1 to T6, which is testing the modality sensitivity. So if you remove the images, will the performance change? Modality necessity, test on visual required questions without images. Format perturbation, which is if you have different answers, so like just shuffle them. If you have in the answers distractor replacement, if you have different, like for example others or unknown, you just replace the others option or unknown and see what happens. And then visual substitution, replace the images with similar but distractor, so false ones, and see if the answer still holds. And then reasoning signal integrity, like ask the model to explain how it achieved its output. So this is a summary of the methods in the paper. And now we can go and view the figures. So this is figure 1, and it's titled Stress Tests Reveal Hidden Fragilities in Large Multimodal Models on Multimodal Medical Tasks. So let's take it one by one, dissect the figure. So you have panel A. It's like we have an iceberg, and okay, what you see in the publications is the great performance of those AI models on medical benchmarks. But actually what's hidden under the surface is most of the iceberg, and those are the fragilities, like hallucinated perception, just making guesses basically, shortcut behavior. It's not really knowing, when you have 5 options, you don't know what's the answer, but like if one sentence too long and you think, okay, it probably is the right answer. And then faulty reasoning, so it gives you an answer, but then why it chose that answer doesn't make sense. So those are the 3 fragilities they're telling us about, but in panel A from figure 1. And then figure B is showing, or like figure 1B is showing some results. So you can see on the x-axis you have the models like GPT-4o, OpenAI O4 Mini, OpenAI O3, Gemini, and GPT-5. Then on the y-axis on the left you have the accuracy, and on the y-axis on the right you have the mean robustness score. And the robustness trend is represented with the red line here, and this line represents the accuracy. So you can see across the models the accuracy is improving, but actually the robustness trend, which is that you can, if you stress basically this model, it holds its performance, its accuracy. This is decreasing, so the robustness trend is decreasing. GPT-4o seems to have like the accuracy and the robustness was okay, but then it decreases with GPT-5, and that is interesting. And the different bars are the different data sets. So, but the trend holds true. And in figure 1 panel C, this is a heat map showing the stress tests on the y-axis on the left, and the heat map is the robustness score, where high is 1 is represented with like faded red, and 0.6 is represented with, which is the low robustness score, is represented with the dark red. I guess what they're trying to show is to put a visual focus on where the model is performing worse. That's why it's more red, kind of. That's the idea. So it's like trying to point out which is the most dangerous model. I think that was the reasoning behind choosing this color. Okay, so as you can see, those are the tests, those are the models again. So each column is the model, and GPT-5 seems to have when tested with a visual substitution, performs the worst, so the least robust when you're substituting images. So you gonna see the visual substitution example here. So yeah, GPT-5 seems to be bad. All models seems to be like not doing well when you're giving an image other than the image that they should be basing their answer on. So if you substitute the image with a different image, still they give you an answer, or so they don't take into consideration the image. So that's why it's not robust. So if you have an image, for example, of a chest x-ray that has a specific anomaly and it gives you the right answer, if you substitute that image with a different anomaly, it still gives you the same answer from the previous image. So it's not really thinking or taking into consideration the input. But GPT-4o seems to be doing well across the stress tests, at least from this heat map, based on my understanding. Let me know what you think. So it seems like GPT-4 is doing well. This format perturbation, so if you change the format, like if you change the numbers or change the, like if you have five choices, if you change their like where they come in or the arrangement, then still like the models seems to be doing well despite the robustness is not changed. So in figure 1D, so that is an interesting, it gives you like an interesting example. Basically, they're showing an example of what's going on. So they're showing an image of a nail to the model with the following question: what is the diagnosis? For example, carcinoid syndrome, dermatomyositis, endocarditis, lesion planus, or porphyria. And the correct answer is dermatomyositis, even if you delete the image and ask the question, GPT-5 still gives you the answer, right? It shouldn't. It should tell you there's no image, or it shouldn't give you an answer. It shouldn't know. It should tell you, like, I don't know, for example, please provide the image. But still, it gives you an answer, and the correct answer based on the image, but in two different setups, like it's not like the same chat or conversation. So it's not like memory from the previous answer. So they didn't ask that and then ask that without the image. Like in different separated tests. And then they ask it to explain, okay, reasoning, the image shows, but there's no image. So the model is saying the image shows changes, discoloration, edema on the upper eyelids, but there's no eyelids, there is no image of an eye, and that was a nail, and there's no image. So hallucinated a reason, basically. So it seems like GPT-5 has issues for healthcare robustness. So let's move to the next figure. And if you have questions, as I said, please put them in the comments and let's have a discussion about that. So the next figure is figure 2, and it's titled Stress Tests Reveal Overestimated Modality Robustness. So it has two panels, this one, and then this is another one, the panel B. So again, on the x-axis the models, on the y-axis the accuracy, and in green this is the data set from New England Journal, and and in yellowish, brownish, or orange is the JAMA data set. So then you have the drop represented when you compare the performance of each model on those two data sets, image plus text or text only. So you take out the image and you give the text only, and you see if there's a drop. And you can see, for example, in GPT-4 there's a drop of, I don't know, 30% on the NetGem, like the New England Journal data set. And the same, so in all of them, when you take out the image, there's a drop in performance. So accuracy drops when images are removed from two diagnostic benchmarks, revealing hidden differences in modality sensitivity across models. Sharp drops on NetGem, but minimal impact on JAMA. That's what we observe here. Like those are bigger drops compared to those here. This suggests inconsistent visual dependence across benchmarks and question types. So basically, based on the data set, then the model performs differently. Light segments show text only, and dark segments mark the drop from image plus text, as we said before. So the right is stress test number 2, which is performance on the 175 NetGem items requiring visual input. So most models exceed the 20% random baseline, even without images, indicating reliance on shortcut cues such as priors, co-occurrence patterns, or memorized QA pairs. GPT-4o performs below chance due to refusal behavior. That's interesting. So they just visualized the drop that happened in right, the drop that happened only in the NetGem group, and if the drop is below 20% or above 20%, let me just see if I get it right. So most models exceed the 20% random baseline even without images. Performance items requiring visual input. So no, that's not the drop. So that's just the performance on the items from the New England Journal benchmark. So their accuracy of the different models that required visual input. And then when they took out the images, still the models, despite no images that the model should rely on to give the diagnosis. Most models exceeded the 20% random baseline. So they performed above chance, meaning they had some idea about the question, even without the needed image to reach that answer. Does that make sense? So let's think a little bit about it. So if you have a question that has an image and you need to reach the answer based on the image, basically, then you look at the image and then you make the answer, and based on that, it's either correct or wrong. But then I give you the same question that requires the image, but without the image, and still you perform above average. You perform above randomness. So it's not like you made it by chance, but you knew something about the answer. So you knew the answer before, such as you had an idea prior, or maybe you've seen it before, or maybe you memorized it, like the same options you had, you memorized them, and then you memorized the answer, basically. So you didn't really think, you didn't answer, you basically cheated, kind of. So the models are cheating somehow. Only GPT 4.0 refused to answer, because which is what someone should do. Like if the question requires an image and the image is not there, you like the sane or the reasonable thing to do is not to answer, refuse to answer. That is why it dropped below the random cutoff point, which is 20% accuracy rate. That suggests a potential memorization. So all the other models seems to have memorized the answer. Only GPT 4.0 was the one that really tried to reach an answer and required the image and refused to give an answer based on that. Interesting. So let's move to the next figure. So figure number 3. Figure number 3 is titled with the following title: Stress tests uncover shortcut reliance under perturbation. So that's results from stress test number 3. And let's read the caption and then go to the figure itself. Option rendering causes accuracy to drop in the text-only setting, solid lines, exposing sensitivity to answer formatting. In contrast, accuracy is stable and improves under image plus text input, dashed, suggesting vision help override shallow textual heuristics. So that is this one here. So format perturbation is what they do with it is when you change the format of the answer. So maybe you change the arrangement, like how it's listed, for example, and then you see if the model still answers. And you have, so here is performance on the x-axis. You have 2 points: the performance on the original before rearrangement, and then here after reordering or rearranging the answers. And on the y-axis you have the accuracy percent. The solid line is the one is the text only. So solid lines are text only, And in the solid line, there is a decrease in accuracy after reordering in the models. But when you have it, when visual input is like the dashed lines, they are image plus text input. The accuracy is stable, for example here, or even improves. The explanation they give that vision helps override shallow textual heuristics. You know, like sometimes we have where the longer answer probably is the correct answer, kind of heuristics, like prior. And seems like in text only options, when you're changing the reordering the answers, this affects the performance of the models. But once you have visual input, this does not impact them. The middle graph, so middle is stress test number 4, is the results for stress test number 4. So it shows accuracy declines as more distractors are replaced with irrelevant alternatives. All models approach random guessing when all distractors are substituted. Surprisingly, replacing a single distractor with an unknown option boosts accuracy, indicating models treat it as a weakened distractor, not as abstention signal. Alright, again, you have two lines, you have two types of lines where text only is the solid, and then text only is the solid, and then the dashed is image and text. So in all of the figures, text only is the solid line, and the dashed one is the image and text. So what they did is distractor perturbation is sometimes you have the one answer that is correct from the 5, for example, options, and then you have 4 other distractors, like wrong answers. And if you change those distractors themselves, the accuracy declines. The more distractors you change or replaced with irrelevant alternatives, then the accuracy declines. But what is happening is when you have one distractor as unknown, so you're reducing the numbers of possible alternative distractors from 4, let's say, to 3, then the accuracy improves. So it treats this unknown variable as not as a distractor, but not like it's not there, but it's as a that it knows that this is really a distractor, you know. So it kind of understands that this is a unknown option, then I should not worry about it. As you can see here, so this is the baseline, this is the before changing the distractors. Here, if you add the unknown, there's a little bit of boost. And then if you have one, I guess, removal or change, second, third, and fourth, in the text only there is a decline. In the image and text there is an improvement in accuracy. Alright, and then the last one is the visual substitution, the or stress test. So accuracy collapses when images are swapped to align with a distractor answer. Despite no textual changes, models fail to revise predictions, dropping over 30%, highlighting brittle reliance on visual label pairings rather than robust visual textual reasoning. So line styles denote input modality, solid, text only, dashed, yeah, all right, we got that. But here we have only visual input, so we don't have the text stuff. And when they remove the images, then the performance drops, suggesting that it memorized the combination of the image and answer, and it's not really performing any reasoning on the new input. One model is interestingly behaving differently, which is again the GPT-4o, this one guy here. The others really dropped. Right, so those are the results of the stress test number 3, 4, and 5. Format perturbation, distractor, and visual substitution. In those two tests, adding the visual input improves the accuracy, but without it, when you're changing the distractor, when changing the format or reordering, then text only, then performance drops. Okay, so next figure is right, illustrative. So illustrative reasoning failure modes. So when the model is trying to explain how it reached its reason, or how it reached its answer, and even the reasoning is wrong, suggesting that it did not reason at all. So it's confident but false heuristic, like it depended on the it depended on something, but not the what is required for it to reach the answer. For example, this one here, where is the diagnosis based on that image? And the ground truth is ocular malaise, and the answering is given a response, for example A, and gave the wrong reasoning. Here, for example, we talked about this, it hallucinated an output without an image, and then basically thinking with image but misgrounded. So the liver is not shown, and visible. Is there biliary tract dilatation? And yeah, so it says no, and which is wrong. Even if it's like thinking with the image, but it's not reaching proper diagnosis. Okay, so that is figure number 4. It is interesting study, interesting paper, showing that so many insightful output. So what we can conclude is that high leaderboard scores is not real world readiness. As you have seen, for me was the most interesting or like understandable and or impressive is that when you even like take out the image. So without an image, even the model tells you that there is an answer and or reaches the correct answer. So that was really striking. And so that means that you cannot really rely on it for like reaching a diagnosis, or you can't rely only on the leaderboard scores that you read about, but you really need to test it on your own data set and on your own patient's population, see if it's really and this also puts value on your own clinical judgment. So for example, some examples I've never heard of before, and for me was difficult to judge if the model reached correct or incorrect. So you really need to have your clinical skills and domain expertise in that field that you're using the AI in, to always calibrate and always make sure that the AI is telling you something that is that makes sense and that is correct. So the other conclusion is current benchmarks overestimate robustness and underdetect reasoning failure. So I think they also suggested, maybe we did not cover it, but I think if you read the paper, they suggested a way of building benchmarks that takes into account clinical reasoning. So that next stage for developing models and test them on data sets or benchmarks that take into account those issues. And what they did exposed hidden fragilities that when you depend on accuracy metrics. So when a model is 80% accurate, but then when you stress test it, you discover that it's not. The authors called for benchmarks as diagnostic instruments, not as goals. So to look at the benchmarks in a different way, not just for scoring, but also that it really reflects the clinical world or what we need in a clinical sense. And then metadata documenting reasoning, visual demands, routine inclusion of stress and adversarial tests in evaluations, then reporting disaggregated context-specific performance rather than aggregated leaderboard averages. So more fine-grained way of evaluating the models that we have. So by this, we're almost at the end of our meeting today, and thank you for tuning in and for staying, and I hope you benefited from this video. At Clinical AI Academy, we aim to improve AI literacy in healthcare by providing high-quality, open-source educational transdisciplinary content focused on artificial intelligence, neuroscience, medicine, psychology, linguistics, and more. We have now on the channel, you can check it, the ChatGPT in Medical Practice course. It's the full course, 30 minutes, gives you how to use ChatGPT in an ethical and safe way in your daily work, from email answering to organization stuff to patient communication, and then as a assistant, or like in your clinical decision support, or in your research. You can all check it out in this 30 minutes video. And then like to invite you to join me next week, where we're discussing an interesting paper, less technical than this one. It's titled Artificial Intelligence for Medical Students, a review of current challenges, opportunities, and future directions, by Chris Patton, and published in the New Zealand Medical Student Journal, September 2025. As always, I would like to invite you to provide your feedback, comments, questions, and also answers to questions I had. We're all in this together. Suggest papers, resources, Join the newsletter on the Substack so that you receive videos, updates, recordings, and events. And you feel more than welcome to join us also on this channel on YouTube. Thank you so much, and see you in the next one.